11 is called Volumes of Solids of Revolution. And within it, we're going to study exactly that. We're going to think about taking a curve, revolving it around a line, and computing the volume of the resulting object. So in this first example, we're going to start with this simple parabola, minus x squared plus 7. Let's sketch that first. This is, of course, just a two-dimensional object, so we can sketch it on the regular set of axes. So minus x squared plus 7 means my parabola is going to have the vertex at plus 7, and minus here indicates that it's going to be looking down. Now it's going to intersect the x-axis at plus and minus square root of 7, which is somewhere around like minus 2.5 of 3, right? So I can place the 2 points here. If I want to be really more detailed in my sketch, I can of course always calculate this at any other points, but I'm not so interested in producing a perfect parabola, just good enough that I can get the feel for what's going to happen when I start rotating it. You notice how I have two sketches, so I'm actually going to produce the second parabola, the exact same one, on my second set of axes, and here we go. In the first one, on the left, let me think about what will happen if I rotate this object around the y-axis, so this way. So now you have to really turn on your three-dimensional thinking. If I take this, imagine like a piece of wire, and I spin it around this way, what is the shape that I am actually getting? It helps to sketch as many of these rotation curves, so to speak, as possible, or as the sketch allows, or as necessary to visualize it, so that you can really picture the object. So first of all, for example, let me connect these two, and I notice that on the back side, I'm going to also get the curve like this. And if I continue thinking about what's going to happen to the points here as I rotate around the y-axis, I can see that what I get is this sort of upside down bowl that the parabola has formed. Now we can of course use Desmos to visualize these things. So here is half of my parabola, and as I rotate it around, it's going to trace this upside down looking bowl that I already have seen in my hand produced sketched, right? So as I make the full rotation, the curve will close on itself and I'll have this object. Now notice here that in this case, I actually only have to rotate half of the parabola, like I started with half, because as it goes all the way around, at halfway, sort of somewhere right here, I'm actually going to see my full parabolic shape. And then as I sweep through, it's going to cover the entirety of my bowl-looking object. Okay, so playing around with things like this will help visualize how we actually build these objects. Now, what about rotating around the x-axis? So now instead, if I take the exact same object, the exact same wire, if you wish, and I rotate it around the x-axis, so this way. Now, again, this sometimes really helps to think about what are the things that will result in me rotating it. And in this particular case, it might actually help, first of all, to think about where is this point going to end up. If I rotate it all the way around the x-axis, it's going to end up at its sort of sister point way down there. So this is probably the first useful point to note at minus 7 here. And I can even connect the two. So this point will get mapped sort of all the way down here and will create this invisible back circle. And then the rest of the points will sort of follow a very similar a rotation. And again, the first few times you draw this seems super awkward and difficult, but the more practice you get with it, the better it's going to become. So now notice that basically what I'm thinking of is all of these points will move down to all of those points, and I'm going to have this like sideways UFO looking shape. Let's take a look at Desmos once again for possibly a slightly better rendition of this. So here's my parabola, and as I rotate it down, so this is going back there, and all the way down as it goes, and then all the way back up to complete my little saucer here. Okay, as I mentioned, and I'm going to say this a number of times throughout these next couple of lectures, visualizing these objects is actually quite a difficult task. So don't get discouraged because you cannot see it right away. This will require practice, and eventually this will become fairly straightforward, but only eventually so. Okay, so as I move this around, it's going to complete the full rotation and end up here. So as I mentioned already, the useful thing to draw is probably the first thing to draw is the parabola, the sister parabola, the one that's exactly opposite of it, to sort of see the full extension of my saucer, and then somehow try to produce the two-dimensional sketch of this very three-dimensional object. This is also why it's difficult, is of course because we're trying to draw three-dimensional objects on a plane. Like I'm drawing it on a screen. You guys are watching this on a screen. Screen is inherently a flat surface, whereas I'm trying to draw on it something that is three-dimensional. So neither of the sketches that we produce are going to be perfect, but hopefully they will be good enough to help us visualize these shapes. Let's try the exact same thing, but with a different curve. So here I have this function, x squared minus 2x plus 2, and I'm interested in it on the region between 0 and 3. So this is what this piece of parabola will look like. And just to practice, I would like to again draw in the same manner as I did on the previous slide with these types of sketches. But now with this function, I would like to draw what that would look like for rotation around the x-axis and around the y-axis. Okay, so let's say this will be the rotation around the x-axis and this will be around the y-axis. So here we will move this around this way, and here we will move this around this way. I strongly encourage you to pause the video now and try to sketch it for yourself, because only by seeing how you can visualize it and what will help you think of what the three-dimensional sketch that this corresponds to, will you actually get better at that. Try this out, come back and see if this worked. Okay, so rotating around the x-axis, what do I have here? I have to take all of these points and rotate them all the way around to the bottom. And each of these points will move to the corresponding point that matches its own rotation. So this is kind of also what is important to recognize is, again, think of physical objects. Think of this as an actual piece of wire, and you'll realize that this piece of wire, when rotated all the way down, will move to be the piece of wire that it's its own mirror image down here. And then all we have to do is sort of produce these lines to make it look a little bit more three-dimensional. So first of all, what I can do is draw this piece that matches my top piece but rotate it around, and then add on likely the end points somehow to make it look and feel a little bit more three-dimensional here. So this is what the rotation around the x-axis will look like. This is kind of like one of those things that Wild Coyote drops on Roadrunner or something like that, right? When rotating around the y-axis, I'm going to encounter something a little bit different. So first, I'm going to do something similar to what I did here. I'm going to take the piece of my parabola and think about where it goes on the other side of the rotation. So if this was my wire and I was rotating around the y-axis, if I was spinning it around, then on the other side, it will end up over here. Okay, so let's draw that first. There we go. And now we're going to talk about something we haven't actually mentioned before, but you might have noticed in the graphs on Desmos. I'm not actually interested in rotating only the wire. If you read the question carefully, it asks to think about rotating the region under the curve. So I am rotating, this wire determines the boundary, but I'm actually rotating everything underneath it in the spirit of integration, really. So I'm going to take this wire and everything that goes underneath it, and this is what I'm rotating all the way around. So in this particular case, I'm going to have these two boundaries because I am actually limited to the region between 0 and 3, and I'm going to rotate this all the way around. So thinking of how to actually visualize this, again, let's draw the boundary cases here, and then let's connect the endpoints, so to speak, right? So on the back here, I'm going to get this, and this is actually going to be a slightly odd shape because what I have to realize is all of this gets rotated, so all of this will get filled out, but what I have in the middle here is actually going to be empty. There's going to be a hole in the middle. So this top piece will get connected. I'm going to have this like odd looking bowl where this inside is empty, but this area under the curve is actually filled in. So this object is really quite difficult to visualize. Let's try to take a look at what both of these would look like on Desmos. So let's take a look here around the x-axis first. So as I went around the x-axis, again, Desmos should give you a feel for rotating the actual area under the curve, not just the curve itself. So as I went around the x-axis, we went all the way down and then came all the way back up. Okay, it might help to play this sort of demo back and forth a little bit, or even better, to pause it somewhere halfway to really absorb the three-dimensional nature of this object, right? So let me go backwards to the original. This is where we started. And then as I rotate around, going to the back first and then coming around to the front, you can see how my solid, because it's actually solid, will get formed once I am back to the beginning. Right? Again, I always think that these objects look more three-dimensional when the rotation is not complete because it gives you an idea of what the inside of it looks like. Now, taking the exact same shape and rotating it around the y-axis is what I mentioned might produce a slightly odd object. So let's take a look at what happens to it here. I'm going to take this, I'm going to rotate it around the vertical axis. So I drag this entire region all the way around. And again, you can see here how you're forming the bowl, but what is more difficult to picture, and is probably clearer on a slice of it like this, is that it's really a bowl. So the inside of it is hollow. And as I make it all the way around, there we go. You can see that the inside is sort of traced by this parabola looking piece that meets down in the middle. Okay, so one more time. Here we go from the beginning. And all the way around the x-axis. Again, let me pause here to make it clear that there is a hollow portion to this curve, and then completing the full rotation. Well, now that we have some idea of what these would look like, let's think about how would we even go about computing the volume of such an object. It's fairly clear that we're going to think about integrals because we are working with the region under the curve, but it's not at all yet clear how they're going to really come into the picture in detail. The first method we're going to talk about is the so-called disk method. And the idea here is all of these volumes that we've just drawn actually consist of disks. So let me redraw the very first example we saw, which was that of a parabola. Disks will work for any kind of rotation, so I'm just taking the simplest example to sort of sketch. And my parabola was the one looking down, and let's say that I consider the rotation around the y-axis here. So my rotation sort of curves produced this bowl looking thing, right? And so the way to think about this shape, if I want to think about it as a three-dimensional actual object, how is this solid really put together? How can I dissect it and think of what the pieces are? So the disk method, which is the first of the two methods we're going to consider, thinks about this shape as being constructed of really skinny disks. So instead of thinking of even just this one curve here, what I can think about is it's actually a little disk. Now I'm going to make the thickness of it negligible so I can then utilize my theory of limits and whatnot, but in itself it's just a little disk. So let me sort of zoom in on this disk and think about how I can compute its own volume. So it's this guy right here, like a really short cylinder, right? Like really short, chubby cylinder. What is the volume of such a thing? Now, the volume of it is actually just going to be the volume of a cylinder, but another way to think about this is the top of it is a circle. So if I have a radius of this circle here, let's call it r, then the top of it is, the area of it is pi r squared, just the area of the circle formula. But then my cylinder has some non-trivial thickness, let's call it h. And so it's kind of like I'm taking this circle and I am bringing it down through h units of height. So the volume of the cylinder is going to be pi r squared h. And the idea here is that this entire bowl-looking shape is simply like a pyramid of these little discs that we're going to add up, whose radius we're going to be able to figure out, and whose height we're going to be able to compute. Now, every shape that we've actually constructed can be thought of as consisting of these discs. So I encourage you to go back through the slides where we've already sketched these solids and think about what are the discs. This is something that we're going to work through going forward. For my real-life analogies of discs, because sometimes it really helps to visualize how to put them together, here are some examples. For example, a salami is really just a composition of a bunch of discs. Each one of these is a slice, kind of like on the pepperoni pizza, right? So if you slice them, you can see that it consists of these discs. But when you have it all in the store, all in one piece, it looks like one cohesive solid. The other way to think of discs is, for example, dumbbells, right? So here we have discs that are clearly different in radius, and if they are made really, really thin, really with small heights, because the height is really this and the radius is going to be here, then what we can see we can form is this kind of like a pyramid that had, it's called truncated pyramid in this case, that does not have the apex at the front. Now, the other one, for example, is a stack of pancakes. This is kind of similar to the salami example, right? You can clearly see what the discs are. You can even see what the radius is. And if they're the same radius, then you're going to get a little cylinder going on. And if they're a slightly variable radius, maybe we have ourselves a little pyramid again. Now, let's think about how can we put all of this together into constructing and actually evaluating the volumes of the resulting solids. So let's take a look at an example dealing with a function that we haven't sketched yet, so we can get both the practice of sketching the volume of revolution and how to compute it. So the function here is square root of x, and we're thinking of it on the interval from 0 to 9. So let's make a quick sketch of what that would look like, keeping in mind that we're going to be rotating around the x-axis, so I'm more interested in the vertical direction rather than the horizontal, right? So I have square root of x. This is my square root of x function. I'm interested between 0 and 9, so let's say this is 9, and I'm going to be rotating around the x-axis. So again, switching on our three-dimensional thinking, I have to take the curve and the region below it and rotate it all the way around, coming out from the screen onto the paper back again and making a full revolution all the way around. So here, what I'm going to have is, the first thing is probably a good idea to once again draw what the sort of mirror image, the extreme case of the rotation would look like. And then think about connecting some of the pieces to really highlight the three-dimensional nature of this object. Once we have these lines drawn in, it makes it a little bit easier to really see what the object in 3 dimensions will look like. So because we're going to be using a disk method, I have to think of, again, this as being composed of these disks. This is kind of like a funky shaped salami, really, right? So if this is my entire salami, then if I slice it with a knife this way, I can see that it indeed consists of these discs that are formed in the middle, whose radii are going to change from very, very small to quite large. So first thing I'm going to do is I'm going to draw a typical disc. And this is going to, again, get easier with practice. But the first thing, I'm going to draw that typical disc on the picture that I already have here so that I can see what that might look like right there. And then in this case, for this first example, what I'm actually going to do is basically take this disc and zoom it right in. I would like a bigger picture of it that I can label. So what happens with this disc is I have my x-axis here. Right, this is my x-axis, and I chose to draw the disc at some point right here where this was its radius. So I can label that point as something. I'm going to leave it as is for now, and then draw the disc that corresponds to the disc of the rotation at this point. So here's my disc. It has some small thickness to it, and there we go, right? So this guy is the same thing, but again, just a little bit zoomed in and without the curve, so I can label it a little bit easier. So now at this point, I'm going to have to label something. Now notice that I'm going to be acquiring these discs all the way down, right? I'm going to start here with a small disc, then my discs are going to get bigger, bigger still, and so on. So they're going to have variable height all the way through, and it depends on what point on the x-axis I consider it at. This is somewhere down the middle or somewhere on my way. So let's call it, let's say, x sub k for some k steps into this rotation process. Now remember that the volume of my disk is going to be pi radius squared times the height. So I also need to figure out what is the radius of my disk and what is its height. So here, what do I have? The radius here, let's think about where that came from on my sketch. So the radius is going to be this. So if I have this point right here, x sub k, and I need to figure out this length, well, I know that this point lies on my curve, whose equation I actually have. So for me to figure out the height, this height right here, that simply corresponds to the y-coordinate of this point. And the y-coordinate can be computed by plugging in the value for x. So I note that for my height here, this guy, all I did was compute the function value at this point x. What about the actual, the radius? I've been calling it the height, right? I mean, it looks like the height on the graph here, but as far as the disk is concerned, its radius. The height of the disk, this guy right here, is going to be something that I want to make very, very small. Because if I make the heights or the heights of these disks very big, I notice that, of course, I'm not going to get a very good approximation of the volume because now I'm going to be missing these like big chunks. I want to make the thickness of the disk or the height of this little disk very, very little. So I'm going to call it, this guy right here, delta x, something small. So now that we have everything labeled, this is my typical disk. What is the volume of the typical disk? One typical disk, I'm not looking at all of them yet. So I know that the volume of the disk is pi radius squared times the thickness of it, that I call delta x. And here I can also then replace the radius by how I've computed it, which was f of this point squared times delta x. Now this is looking pretty bulky, but don't worry about it for now. Let's just take our logic through even further. So now I have a volume of this one disk. Well, that's not quite what I want. I don't want the volume of just this one disk. I want the volume of all of these disks added up as they get built from 0 all the way to 9. We need to sum all the volumes from 0 to 9, and along the way, what I actually want is the thickness, the heights of these disks to be very, very small number. So let's record that and think about how we can put all of that together. So as I keep this in mind, let's try to write this exact expression in mathematical notation so that I can figure out how I compute the total volume. So first of all, I noticed that I want the delta x's to go to 0, so I can immediately introduce the limit as delta x goes to 0, and then I need to sum the volumes of all of the typical disks. So I have a sum. Let's recall our summation notation. My sum needs to go from 0 to 9, and all I need to sum are the actual volumes of typical disks. So all of these guys. So pi f of x sub k squared delta x. And just before you are beginning to really get worried about how on earth are we going to calculate this, we can just stare at this expression for a while and recognize that this is exactly the definition of the definite integral, right? Remember when we were first back quite a few weeks ago, when we were first looking at the integral and we were computing this as the sum of the rectangles that represented areas and then taking the limit as the width of those rectangles was going to 0. This is exactly the same thing, but a three-dimensional analog of it. So this is nothing else but an integral from 0 to 9 of whatever happened to be inside my summation, where xk's simply become x's and delta x simply becomes my dx. So in this case, all I'm going to have then is pi f of x all squared times dx. Okay, so notice here that again, xk's simply became x's because the summation became an integral, and delta x became dx because once again, the summation became the integral. So in my particular case, now all I have to do is replace the function f of x with the function that I'm actually working with, which is square root of x. So what I have is the integral from 0 to 9 of pi, my function, which is root x, and then I have to square it because that was present here, and that came from the fact that the volume of a typical disk is pi r squared, and then dx. Now you notice that this integral, of course, is very easy to compute. Once I actually bring the square in, I simply get the integral of pi x dx. I can easily evaluate its antiderivative and then plug in the limits of integration to produce an actual number. I encourage you to finish this off, but the idea is that with these computations, with these volume problems, the hardest thing is to set up the integral. The evaluation of the integral is actually usually fairly straightforward. So let's try to do this again, but on a different shape. Let's take our parabola that we have seen before, and again, think about rotating around the x-axis between 0 and 3. So once again, I'm going to produce the sketch that I've already produced before, but now this time also supplemented with a typical disk whose volume I will now have to really produce. So again, this guy, to make it look three-dimensional, looks something like this, rotated the x around the x-axis. And now what I'm going to do is go somewhere in the middle, let's say right here. It really doesn't matter where you go. But in all of these questions, you really have to draw in the typical disk so you can see what your corresponding radius and corresponding height will actually be. Okay, so once I have this disk, what I can right away say is that the total volume of this shape, no matter what the shape is always going to be pi, my function that corresponds to radius squared times dx. So let me just make it very clear here that this has to correspond to the radius of my typical disk, because this is really the actual formula, pi radius squared and then times the height of the disk summed over all the disks that get built along the way of forming this volume of revolution. Okay, now I have to think about what are my radius, what is my height, and where do I go to and from. So in this case, this is fairly straightforward, right? Because I can see, of course, that the radius here matches the actual function. It gets built as the function does, and we'll see later how that might be different. So my function here is x squared minus 2x plus 2. The radius has to always get squared, dx. And now my integral is in terms of x, and I'm asked to go in terms of x's between 0 and 3. So this is my integral that, when evaluated, will actually give me the volume of this solid three-dimensional object. Okay? Let's take a look at another example here. Let's in fact take a look at a really nice example, for example, a sphere. A sphere is a beautiful object that can be thought of as rotating half a circle around either x or y axis. So here, let's think about rotating this half a circle around the x-axis. First of all, take a second and really persuade yourself that what you're gonna get is a sphere, right? Think of these, I used to bring these to class, these Chinese lanterns that you can get that are actually flat, and when you unfold them, you rotate them out, you get these like honeycomb paper within, but they actually, once unfolded, they will actually produce a sphere that you can then hang for decorations. Okay, so again, as a first step, it's best to draw the other extreme case. So what will happen if the rotation is carried out all the way down? Here we go. Let's pretend that this is exactly the same as the top circle here. I realize that it's not the prettiest. And then to think about this solid as being composed of disks. So let's say I'm going to take this ball, this sphere, let's think of it like a dough ball or something, and I'm going to cut it this way with a knife. The typical disc that it will produce is something that I'm interested in sketching. So I will draw this little disc that I will get somewhere there. There we go. I guess I know that it's on the inside, so I don't have to try too hard to make it appear like that. Maybe I can even draw on the other side of it so you can see that it's actually a disc. Okay, so this is my disc. One thing I noticed right away is, of course, that the thing that I want to be small, which is the thing right here, is going to be parallel to the x-axis. So this is going to become useful later. This is something that I'm going to decide whether I will set up my integral in terms of x or in terms of y. Here I notice that the thickness of my typical disc spans in the direction of x, and therefore I will label it dx. One thing I need, though, is the equation of this curve, which I don't yet have. So let's recall what the equation of a circle actually is. And digging through your calculus, pre-calculus memories, you might remember that it's x squared plus y squared is equal to r squared if it's centered at the origin. So this will give me a circle of radius r. So r and negative r here, centered at the origin. Now, I don't really need, or rather, I don't really want this expression. What I really want is y equals something. So I'm going to solve this for y, and I notice that I will get the plus and minus square root of r squared minus x squared. The plus will correspond to positive values of y, which is the top half circle, and the minus will correspond to the negative values of y, which is the bottom half circle. We already noticed that I only had to rotate the top half to get the full circle, so I am going to be working with the top half of the circle, top half circle, which means that I can take my square root to be positive. Excellent. So now let's think about what is the volume of this resulting thing. So I'm going to have myself an integral of pi r squared, where r is the radius of my disk and the height of my disk here. So I guess I can actually write it this way to make it a little bit different from how I've written it down last time, which now means I get to replace all of the unknowns, namely the radius and the height, with what I see in my picture. So this is why it's crucial to actually draw in the typical disk, because it's the only thing that will allow you to decide what is your radius and what is your height. So do not skip drawing a picture, because either you're not good at drawing pictures or whatnot. If you don't draw the picture, you're almost guaranteed to not be able to decipher this correctly, okay? The picture no matter how bad it is better than no picture at all. It's the only way really to produce the radius and the height consistently throughout all of the examples. So here, this is my typical disk. I notice that the radius of it is exactly what will happen if I plug in this value for x into my function. This is going to give me this vertical height of it. So the radius here is my function itself. So what I'm going to have is pi, and then I plug in my function squared. And then the height of my disk, which is this thing right here, we already discussed how because it's in the same direction as x, it's parallel to the x-axis, that's what's going to correspond to dx. Okay, so once again, because it's our first example like this, let me label this here again. This is the radius and this is the height of my typical disk. Okay, pause the video here, let that really sink in, to make sure that you understand where this formula came from. Okay, now what are my limits of integration? My integral is in terms of x, which means I have to think of the smallest and the largest x on which I care about, right? And I can see here, of course, that my circle goes from negative r, because that's the radius to the left, to positive r, which is the radius to the right. From negative r to r. And in this example, I'm actually going to go through the trouble of evaluating it just to see what is the answer that I end up with. So one thing that I can notice right away if I am to evaluate this integral is that because the circle is so symmetric, I don't really have to go from negative r to r. I can go from 0 to r and then double the result, right? I can see that the rotation on the left here and the rotation on the right will produce the exact same shape, but mirror image of it. So I also know that plugging in 0 into the integral is easier than plugging in any negative value. So this will probably result in easier algebraic manipulations. And then I can, of course, also notice that once I multiply or exponentiate the square root here, the square root will go away. So I'm going to get r squared minus x squared dx. And now it's a matter of simple antiderivative taking. So I can leave my 2 out here. I can even leave 2 pi out here, really. And then what am I going to have for the actual antiderivatives? First of all, I have to take an antiderivative of r squared. Now remember that r is the radius of the circle, so it's a constant. I'm taking it with respect to, I'm integrating with respect to x. So this is like taking, antiderivative of 5 squared dx. I leave my constant and I will simply tack on an x to it. And then I have a minus here, and then I have to take an antiderivative of x squared, which is x cubed over 3. Okay, pause here for a second, make sure that this is all right. Again, all I did was take pi out to join the 2 here because these are both constant. And then I needed to take an antiderivative of r squared, which is r squared x, and then an antiderivative of x squared, which is x cubed over 3. Now, I haven't actually evaluated this. I need to do this between 0 and r. So what am I going to get altogether? Remember, I plug in the top first in for x, and then minus, and then I plug in the bottom. So on top, I'm going to get, remember, I plug in r for x, so it's going to be r squared times r, which will give me r cubed. And then I plug r here for x, which will give me minus r cubed over 3. And then I subtract the same expression, but plugging in 0 for r, or for x, sorry. I plug in 0 here, I plug in 0 here. Well, multiplying 0 by anything will produce a 0, so I notice I have 0 minus 0, so this will be times 0, which of course means this whole thing is 0. So what do I get here altogether? I'm going to get 2 pi times, and then I have r cubed minus r cubed over 3. So this is like an apple minus a third of an apple will give me 2/3 of an apple, 2/3 of r cubed. And now, moving things around, like the numbers joining the numbers up in the front, 2 times 2/3 is 4/3. And then what do I have? Pi r cubed. Pi r cubed. So this is my final answer for the volume that I was constructing. Let's take a step back and think about it for a second. What did I get? I rotated half a sphere, the top half of the circle, to obtain the volume of revolution from it. This resulted in a sphere. I've broken it down into disks that it was composed of. I evaluated what is the radius and the height of a typical disk. I added, with integration, all the disks from negative r to r, and then actually proceeded to integrate. And in the end, my answer was 4/3 pi r cubed. Does that seem familiar? 4/3 pi r cubed. Of course, this better seem familiar. That is exactly the volume of the sphere formula that you've always been told as an undisputable fact. So let's just take a second here and marvel at the fact that we have in fact developed tools that allow us to derive formulas that we always thought were just there for us. Let's now take a look at another example of how to use disks to compute the volume of revolution rotated around the y-axis. All of the examples we've seen so far have been around the x-axis. We will see how it's really easy to actually state this result in an analogous way to be around the y-axis. So here I am asked to rotate around the y-axis the region bounded by y equals 1 minus x squared and the axis. 1 minus x squared is a parabola, shifted one up, looking down. So let's first of all make a little sketch of what we are rotating. Again, remember that we are going to have to sketch in order to figure out what is the typical disk and what are even our limits of integration. So take your time, produce a reasonable sketch. It doesn't have to look terribly three-dimensional, and try not to pack it with too much information, but just enough to see what your disks will be. So 1 minus x squared, let's say this is up at 1. So I'm going to have a parabola that looks like this, and I'm going to rotate it around the y-axis. So now I'm rotating not around the x-axis, but around the y-axis, which means that I will really be joining these ends here and producing this kind of like a bowl looking thing that we've seen before actually, right? So now again, I'm going to try to draw in a typical disk on the way. Now, because it's a rotate around the y-axis, it's kind of like I am cutting, and you can already see in producing or in trying to produce a three-dimensional looking thing, I'm going to be cutting this way in order to see what the disks actually are. So I can see that here my disk will span along the actual y-axis and look like this. And this is going to be the major difference between the two the rotations around the two different axes. Notice that in the previous example, my disk spanned, like it was centered on the x-axis, and it was sort of rotated around the x-axis, right? Which also meant that its height was parallel to the x-axis and expressed in terms of x. In this example here, it's centered on the y-axis, it spans around the y-axis, and its thickness is parallel to the y-axis, which means that its thickness is going to be expressed in terms of y. Okay, so that means that for my volume, I'm going to leave myself a little bit of room here, you'll see in a second why. For my volume, I'm going to need the integral of pi r squared h, like before, and now I have to figure out what my r and my h are. So the radius of my typical disk is going to be this guy right here, and that's going to be my function, right? It's going to be my function, except for now everything is flipped. It's a little bit different, right? I have the point on the y-axis, and I have to calculate the radius as its x-axis component. So it's not going to be the function evaluated at x like it was in every case up until now. It's going to be the function evaluated at y, because this is where my disk is centered. So the radius here is going to be the function evaluated at y, and the height here, which is another clue of the fact that everything has to be in terms of y, is what we've already determined, right? The height of my disk spans along the y-axis and therefore has to be in terms of y. And now I face a little dilemma because I need my function in terms of y, but I have it in terms of x. So before I can plug it into my integral, I need to solve this for x instead of for y. So let's do that first. If I start with y equals 1 minus x squared, I need to express it, I need to isolate x. So I'm going to have x squared is going to be 1 minus y squared, which means that if I take a square root, I'm going to get plus or minus square root, oops, I acquired an extra square here, 1 minus y, and now I have to decide, do I take the positive or the negative? And it's kind of like the same exact thing as with the circle and sphere example. If I take the positive, it means that I'm taking only the positive x's, and the positive x's are going to be in this direction, so that means that I'm taking only this piece of the parabola, but when rotated, that will be enough to produce the entire solid. I can of course also take the negative to be this portion. This rotated will also produce the same volume. I only need to take one of them, so I'm going to take the positive. So let's see, what do I have in terms of my integral then? I have pi, my function, this guy, squared. So pi, my function, 1 minus y squared, square rooted squared, times the height of my disk, which is dy. And now I need to figure out what are my limits on this integral. It's again key to recognize that it's in terms of y. So that means that the limits have to be the smallest possible y can be and the highest possible y can be. So I'm looking at the y-axis for this. The smallest is going to go from here, so from 0, and the biggest one, well, my parabola ends here, so it's going to be at 1. So from 0 to 1. And this is now my integral. We can perform the integration the exact same as we normally would. So you will first of all exponentiate this root. You will basically get rid of the root, which is why it never actually mattered where you took the positive or the negative. And after you integrate, anti-differentiate and whatnot, you should get, according to my calculations, pi over 2. So go through, see if that's the answer you get. Let's now summarize what we have seen with disks. We have seen basically two different ways to use disks, and that is to rotate around the x-axis to produce the volume of revolution, or to rotate around the y-axis. And in each case, the formula, so to speak, was a little bit different. So let's just make sure that we can generalize and then be able to use this general setup to compute specific integrals. So when we rotated around the x-axis, first of all, this is what we got. This was my function f of x, and I have formed disks to be centered on the x-axis. Now that also means, though, if this is the center of my disk, then the radius of it was what corresponded to the function, and the thickness of it here spanned along the x-axis, and therefore is what corresponded or what contributed to it being called dx. So when we rotate using disks around the x-axis, we end up with the integral in terms of x. So what I'm going to have is pi, my function in terms of x squared dx. Okay, and in terms of where it goes to and from, take a look at the smallest possible x value and the largest possible x value. So in this case, they're called a and b. When we rotate around the y-axis, it's going to be very similar, but now we're going to have to sort of flip our thinking to be along the vertical axis. Now, this was my function, f of y in this case, right? So this was the function. When I rotated around the y-axis, I recognized that the disks have to be centered on the y-axis, which means that the radius had to be computed given the y value to figure out what the radius would be here, and the thickness of the disk, its height, now was parallel to the y-axis and therefore is described as dy. So when we're using disks around, rotating around the y-axis, the integral is going to be in terms of y. This is a nice shortcut to remember. So here I'm going to have pi f of y squared dy. And again, think of what is the smallest and the largest y value is going to be, whatever they happen to be in the problem. Here we're calling them a and b. So just a little thing to remember, when rotating around the x-axis with disks, you're going to get an integral in terms of x, because the thickness of the disk is what spans along the x-axis. If you're rotating around the y-axis, the thickness, the disk will be centered on the y-axis. The thickness of the disk will be in terms of y, which means that the entire integral is going to be in terms of y. This is nice to remember when we're rotating just the y-axis. In a few lectures, we're going to see examples when we're rotating around other lines, and that's when it's again going to be essential to be able to draw reasonable typical disks and think about what the radius is. When rotating around the axes, these two formulas will do the trick.